Hey everybody, Dr. A here, and in this video we're going to be exploring another example of using the double integration method. So let's go ahead and get started. In the given information, we're being told to use the double integration method to derive the equation of the elastic curve for the loaded beam. And we're being told that the flexural rigidity, that's the product of E times I, is a constant. So in the given figure, we have a simply supported beam that is supporting a uniformly distributed load over its entire length, and its entire length is called L. And we're also being given an origin at the left support with positive X pointing to the right. Okay? So let's go ahead and figure out how we're going to tackle this problem. So under solution, the first thing we need to recognize is what are our governing relationships when using the double integration method? Well, from our previous video, we know that EI, which is the flexural rigidity, times theta is equal to the single integral of the moment function dx. Okay? We also know that EI times the deflection delta is equal to the double integral of m as a function of x dx, and this can also be written as the single integral of theta as a function of x dx. So all of this is function notation. It's not m times x, it's m as a function of x, all right? So ultimately, what do we need? Well, we really just need to get moment as a function of x. That's really where the work is going to be in these processes, okay? And once you get that moment function, then you pretty much are ready to go, all right? So let's go ahead and do that. For our simply supported beam, hopefully we can go ahead and obviously tell that when we have a loaded simply supported beam with a uniform load W on it, then you're going to have a vertical reaction at both ends, and of course you have a horizontal reaction AX, which is 0. Now, what are the reactions here? Well, you can use equilibrium equations, but hopefully we're comfortable enough to say that this is just WL over 2 at each of the reactions, okay? And again, this entire length is L. So what we really need is the moment function, right? So we're going to use method of sections, all right? We're going to say MOS, and what we're going to do is we're going to have a little segment of this beam, and again, it's got W on it, and we've made a cut section here. Now at that left support, we have WL over 2, and this is going to be cut at a distance X away from the support. And what's going to become visible here? Well, we're going to have a shear force V that's visible, but more importantly for this application, we have a moment function M that's going to be at that cut, okay? And so then we're going to say sum of the moments about the cut equals 0. And then looking at this method of sections free body diagram, we can see that we have negative WL over 2 times X, and then plus WX times X over 2, and then plus M equals 0. And we can do some rearranging, and we can write the moment as a function of X is going to be equal to negative WX squared over 2 plus WL over 2 times X, okay? And again, this is moment as a function of X here, all right? And so what have I done here? Well, I've only done method of sections. I've just written a moment function. We already know how to do that. We've learned that in our previous lectures or our previous videos, all right? So nothing new so far. So what do we do next? Well, now we take this moment function and we integrate it the first time to get our theta function, which is our rotation angle, and then we integrate that to get our delta function. So let's do that one step at a time. So the first integration is going to give me basically theta, right? So I'm going to say EI theta is equal to the single integral of that moment function. So that's the integral of negative WX squared over 2 plus WLX over 2 dx, okay? Now, when you integrate that, this is a simple polynomial function. So your variable, your independent variable is just x. Everything else is a constant, right? So this is going to integrate to be negative wx cubed over 6 plus WL x squared over 4 plus an integration constant C1, all right? Now what we're going to do is we're going to integrate that one more time, and that's going to give us our delta function. So we're going to say EI delta is equal to the integral of this whole term, right? So that's going to be the integral of negative WX cubed over 6 plus WLX squared over 4 plus C1, and we're integrating that with respect to x. And so again, it's a polynomial, so it's a simple integration. We should end up getting negative WX to the 4th over 24 plus WLX cubed over 12 plus C1x plus C2. So we generate a second integration constant here. So we've got two integration constants we've got to deal with. Now, from our previous videos, how do we deal with those integration constants? Well, we apply either boundary conditions or continuity conditions, okay? Now, we should know from our previous videos, boundary conditions and continuity conditions are similar, but they are different, okay? In this case, in our original figure here, do we have any continuity conditions that we need to be using? Maybe pause the video and think about the answer to that. Do we have continuity conditions here that we should be using? The answer is no. We only have boundary conditions. In particular, we have two boundary conditions at the two boundaries, right? So the deflection at the pin should be 0, and the deflection at the roller should be 0, all right? So how are we going to express that? Well, we're going to write BC, all right? And we're going to say the deflection at x equals 0 is 0, and we'll call this boundary condition number 1. And then the deflection when x equals L is also going to be 0. That's boundary condition number 2. And so what we're going to do is we're going to utilize these two boundary conditions in the second equation that we just developed, that we just integrated and got, okay? Why? Why are we only using these boundary conditions in this second equation? Well, it's because these boundary conditions have to do with delta, which is a deflection, and that second equation is a deflection equation, right? So here's what we do. We're going to substitute these values in. So let's first use boundary condition number 1. I'm going to say EI multiplied by 0, right? So this right here, this 0 is delta, okay? This delta equals 0, and then we're going to say equals, and we're going to plug in or substitute in 0 for all the x values, right? So negative w times 0 to the 4th power over 24 plus WL times 0 cubed over 12 plus C1 times 0 plus C2, and then that clearly yields a C2 value of 0, right? Because all three of these terms 0 out, and the left side of the equation is 0, so C2 equals 0, all right? Now we're going to use boundary condition number 2, all right? So same equation, we're going to say EI times 0 equals, and this time delta is 0 when x is equal to the full length L. This is on the right side of the beam, all right? So we're going to say negative W times L to the 4th over 24 plus WL to the 4th again over 12. Why is that? Well, look back at this second term here. You have L times x cubed. We substitute L into the x value and we get L cubed. So L times L cubed is L to the 4th, all right? And then we're going to say plus C1 times L, all right? And C2 was already 0. We figured that out in the previous step. So we're going to do some rearranging here, and we're going to be able to solve for C1 with just basic algebra. C1 should be negative WL cubed over 24. All right, so maybe pause the video and do your algebra rearranging here to make sure you get the same term that I got. And then finally, we can take these two values of c, c2 is 0, c1 negative WL cubed over 24, and we substitute them in to this delta equation here, and that becomes the equation of the elastic curve. All right, so if I do that, then I can say delta equals 1 over EI multiplied by negative WX to the fourth over 24 plus WLX cubed over 12 minus WL cubed over 24 times X. Now you can stop right here. This is sufficient to answer the question. This is the equation of the elastic curve, which means that this is the shape of the deflection diagram. All right, so this is fine to stop here. Now, often we see a lot of these elastic curve equations packaged a little bit more conveniently. And so if you were to look in a textbook, namely the Hibbler Mechanics and Materials textbook, but if you were to look at most Mechanics and Materials textbooks, you would see this equation kind of algebraically rearranged as the following. A lot of textbooks like to factor out common terms, and so you might find this as expressed as negative WX over 24 EI multiplied by X cubed minus 2LX squared plus L cubed. Now you might be looking at this and you might be saying, well, wait a second, how are these the same? Well, what happened and what a lot of textbooks tend to do is they'll factor out terms. So if you factor out a negative W over 24 from each of these terms, what do you end up left? I'm sorry, negative W over 24 times X. Factor out one of the X's as well. What do you end up with? Well, we factor out this negative WX over 24 and EI, let me highlight that again, negative WX over 24. EI was already pulled out. And so if you factor that out, what do you end up with? Well, you end up with an X cubed left in the first term. You end up with a negative 2LX squared in the second term. Why negative? Well, you're pulling out a negative from all three of these terms. And then you end up a plus L cubed as that third term. So what I would encourage you to do is maybe take a second, pause the video, and you know, do this factoring yourself. Okay, let me back up some of my highlights here. But do this factoring yourself. Convince yourself that this is algebraically the same. Now you might be thinking, well, Dr. A, you know, we've got computers that can do a lot of this for us. We've got applications, different apps that can factor for us. Why do I need to know that? Well, as an engineer, you need to understand where this stuff comes from and why it works the way it works, okay? Anybody can push buttons on an application, on a computer, or on a phone, right? But as an engineer, you have to understand where this comes from and why it works. And the only way you're going to do that is if you do the math yourself, all right? So that's what I encourage you to do. Hopefully this video was helpful to you. If so, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.